Good afternoon, everybody, and welcome to this online technology meeting on fiber sensors for industrial applications. My name is Antonio Castello. I'm technology manager at EPIC, and it's a pleasure to be here to talk about this interesting topic, fiber sensing. Focus today in industrial application is something that a kind of technology that can be used for different type of applications. Structural health monitoring is one quite traditional as well, but today we want to focusing more industrial related topics, and we will have a great set of speakers to discuss about new developments, new solutions, also examples of applications, fabrication methods as well, and we will end the meeting with overview of trends, opportunities in this interesting market with the expert Alexis Mendez. So for me, it's a pleasure to introduce you EPIC, that is the consortium of more than 800 companies related with photonics technologies. Our goal is to help our members to connect with people, to learn about new markets, to discuss about potential applications and future trends and opportunities, and also to help with other business-related needs that our members can have. This is a short summary of all the benefits that we offer to our members. So discuss about technology that, as we are doing today, and networking, that is another topic that we want to have today. So after the presentation, we'll have time for questions and answers. So please raise your hands virtually in the Zoom chat or write also in the chat to discuss about your interests and your questions. What is your doubt? What is your doubt-related application? Because the networking is what we are here to talk, to learn about the others, and to discuss about potential collaborations. We also offer access to different market reports in our members. In fact, we had one from last year from Alexis as well that was also going deeper into all the opportunities related with the fiber sensing in general, what is new in terms of the companies and manufacturing solutions and opportunities in the market. And then, as I mentioned, we help also with human resources, contact with investors, all the topics that could be interesting for our members from a business point of view. So if you have any need, any non-solved issue, please contact us. Here you have my email address and also the general email address of EPIC. So feel free to drop us an email and share with us your doubt. And as I mentioned, networking is one important activity for us, and also the technology discussion that brings these networking events. So I encourage you to go to our website and check what is happening in the next weeks. I will perhaps highlight a couple of physical meetings that we will have. One is related with photonic integrated circuits, because fibers are quite active there, and also sensing solutions. So if you're interested in joining this meeting in Lausanne at Tech facilities to discuss about how fibers can be involved in the photonic integrated circuits solutions that are quite powerful nowadays, very interesting for medical applications, in the semicon, in consumer electronics as well. Do not hesitate to check the website and register. And of course, we will be again in San Francisco at the OFC. So we will organize a member lunch, networking reception, different networking activities. So if you are participating in this exhibition, check the website and join us for one of or several of the events that we will have there. And of course, in the next week, we will continue with the online meetings as we are doing today. For tomorrow, we have new product releases. Tomorrow, new product releases in today's market report on semiconductor-related industry, and then we will continue with other technology meetings. One could be interesting in photonics for geological and mining applications, where sensing can also be a relevant technology. And also in specific about the general meeting, because it's where all the EPIC members and also companies outside the consortium can discuss about business opportunity, strategy, markets. This is a C-level event where people from different companies will be open to discuss about trends in the markets, which opportunities are in the different sectors, discuss about interesting collaboration in the technology point of view. We will also have investors and venture capital companies to discuss about potential business opportunities and investment opportunities. And we will learn about the Spanish photonics ecosystems. Every time we go to a new country with our general meeting, we try to bring all the EPIC members, local EPIC members in the country to discuss about what are they doing, the technologies that are prominent in this region. So it's a good opportunity to have a few days in a very nice environment and with a good discussions. So I encourage you also to check the website, see the agenda that is quite nice, and join us in Barcelona for this annual meeting. And for today, we have a quite nice amount of registrations, a lot of people interested in this topic and covering all the supply chain slots. We have companies that are covering as equipment manufacturers, but also components. So a lot of companies developing fiber bragging solutions or related components, fiber manufacturers as well. Of course, end users, integrators, companies that are offering service, metrology and testing solutions as well, and software and development. That is, I think, very important in this fiber sensing and analysis of the information. Of course, as always, R&D centers and organizations are very important for the development of new technologies. And I want to finish with agenda for today. So we will talk about, as I mentioned, about different topics. We have a couple of examples of a use case of the sensings in wind turbines and also in the industrial generators. We have the point of view of Schütte and Proximion as manufacturers of sensing solutions. We will also learn about the fabrication of Bragg ratings using femtosecond lasers. A point of view a little bit different as a sensing solution based on micro-optics attached to the fibers by Keystone Photonics. And as I mentioned, we will finish with this overview of the market by Alexis Mended. And that's all from my side. So I would like to invite Christian Nielsen, is the CTO at Schütte, to talk about their solutions based on polymer optical fibers and understand where can they be used from an industrial point of view. So Christian, the floor is yours. So feel free to share your screen.
Thank you, Antonio. Thank you for that very nice introduction. I am very happy for this opportunity to introduce you all to our company, Schütte Sensing Solutions, our technology and some of our products. So my name is Christian Nielsen. I am the CTO of the company and one of the founders. And I have a background from the Technical University of Denmark. And Schütte Sensing Solutions is also a spin-out from the Technical University of Denmark. We never moved far away from home because we are now located only 30 minutes north of Copenhagen. We're a small company. We like to think of ourselves as a mature startup. And here's a family photo of us. And it can be hard for me to believe, but next week we will turn 10 years old. And with that, we have been on a journey from taking our technology from the lab to now offering it to multiple industries. So let me talk a little bit about our technology first. So we do polymer optical fibers, and with them we can offer a sensor that is very sensitive to stress and has a very large strain range. It can measure humidity and it can measure temperature. And from those three parameters, we get our name, which is strain, humidity, and temperature. And yeah, being around for 10 years, we've also been able to demonstrate our technology in many industries. So we think of it as a fairly well-established technology. We've applied it in the construction industry, in the medtech industry, and in the energy industry. I'll get a little bit back to that in a minute. Further on our technology, we make our fibers out of polymer, but we use the microstructured fabrication technique. And as you can see in the top left corner, there's a scanning electron image of the end facet of the fiber. We have 36 holes running through the length of the fiber in a lattice arrangement, and in the center there's a hole missing, and there where the hole is missing, that's the core of our fiber, and that's where we capture light. So using microstructure or photonic crystal technology like this enables us to make our fibers single mode. It also makes it possible to make fibers without any doping. So we can use pretty much any polymer. Our only requirement is that it's a thermoplastic, and it's fairly transparent. We manufacture all of our fibers in-house. We use the drill and draw method, where we use a CNC machine to drill the holes in the pattern that we require, and then we have 2 draw towers to stack or to scale the fiber down from a 60 millimeter preform down to a hair thin fiber or any dimensions that we want. Well, this fabrication technique was developed at university, so there's nothing new there. Our mission has been to take this technology from the lab and make it mature enough to go into industry. And 2 of the biggest barriers that we identified early on was the handling of the fibers and the cost of instruments. Now, the handling of fibers involves simple things such as putting a connector onto the fiber, putting protection and housing and adhesive methods or barriers for moisture or other handling mechanical aspects. And this, of course, is continuously going on. The other aspect is the cost of instrument. Our sensing system is based on fiber Bragg ratings. So in our polymer fibers, we will use the UV laser and a face mask to write fiber Bragg gratings into distinct points along the fiber. Each fiber Bragg rating is a sensing element, and the unique property of fiber Bragg ratings is that you can put many FPGs on the same fiber, so you can have a whole series of sensors on a single strand. Now, in order to interrogate these fiber Bragg ratings, you need a light source and a spectrometer. And part of our mission has been to lower the costs of these instruments. And our latest Contra system is now down to 2,000 euros. I think that this is a very interesting problem, and I know that there are other companies working on this as well. So I look forward to actually getting that cost down, because the lower the cost of the instrument is, the more markets we can address, the more applications we can address with our technology. Now, the sensors themselves, being made of polymer with a FPG in them, really enable us to utilize the benefits of polymer optical fibers, such that in the sense that the polymer can be, the polymer is much more soft than a glass fiber. Glass fibers are notoriously very stiff and hard to work with, and they break in a shattering method, whereas polymer fibers are much more flexible and can be more easily stretched and have a different failure mode. The low Young's module of polymer fibers makes them ideal for picking up very small stress levels, and also makes them compatible with soft materials. So we have some applications where we embed our fibers into rubbers or into carbon fiber elements, plates. And in that sense, we offer new optical strain gauge capabilities to places where you maybe couldn't go with glass fibers because of their inherent strength. On top of strain sensing, our fibers have a lot of traction as humidity sensors, which is also a fairly unique capability to polymer fibers, because they are some polymer fibers are inherently absorbent of humidity, and that makes them very good as humidity sensors. We have our own sensing system that we have developed called Contra, but we've also seen a pull for making optical sensors that are compatible with C-band equipment. And these kind of sensors we see as a complement to silica fibers, to glass fiber sensors, such that you could have a daisy chain of silica fibers, and at the end you could have one of our polymer fiber sensors as a humidity sensor. We have the big advantage of using the polymer fibers as humidity sensors is that they are much more robust with regards to very high humidity levels. We can leave them in water for months, and afterwards they will still function after they dried off. There's no drift and there's no lock-in problems, as you might see with the electronic humidity sensors. And they are fairly compatible with many harsh environments. And being made of polymer, the sensors themselves, they do not corrode and they do not conduct electricity. We have a few applications running with these kind of humidity sensors, and we have envisioned them being used in structural health monitoring, but also for critical infrastructure on pipelines or in tunnels, where you want to make sure that there's no ingress of moisture. They can, of course, be customized to different kinds of housings and different kinds of membranes that we can put onto them. The last thing that I would like to mention is that we are also offering chirped fiber Bragg ratings. These chirped fiber Bragg ratings are a fairly novel technology from our side, where we can make up to 100 millimeter long chirped FPGs. And these offer unique properties when it comes to detecting fast events, such as detonation fronts or shock waves in materials. And again, we utilize the unique properties of polymers, being that they have a much lower mechanical mismatch with as compared to glass fibers. But this technology has already been demonstrated by the nuclear research facility in France, SEA, where they've done shock wave detection using our fibers, where we're basically using the polymer optical fiber and basically the destruction of the fiber for timing the arrival of the detonation waves. And then this kind of technology has a lot of promise, as well as maybe in other kinds of structural health monitoring, as in small solid rocket motors and stuff like that. I think with that, I will finish my small presentation. I look forward to your questions.
Thank you very much, Christian. So as I mentioned, we have time for questions after this presentation. So you can use the raise hand button in this screen, or use also the chat to write your questions. Perhaps you can talk a little bit about these two epic questions that you include, Christian, in the last slide. That what can the others do for me? What can I do for the others? So what kind of cooperation, collaboration are you looking for?
Well, we see this technology as sort of a platform technology, and it can go to many industries and a lot of applications. And we don't necessarily have the capability to address all of those markets ourselves. So we're very open to partnerships. We have partnerships with companies where they want to go into specific application areas, and we would like to be able to enable them to make either to expand their current portfolio, or to also offer new type of sensors.
And I have another question regarding the measurement of humidity. Is there any potential source of error with other liquids or other kind of components that can include some of the elements that are also in the water? How do you see the measurement in the industrial, in the pipes that you mentioned, for example?
Yeah, I mean, we are using off-the-shelf polymers such as PMMA or PC. So they do have some cross sensitivity to other solvents, but those are kind of an initial screening can be done by just looking at the polymer database to find out what exactly they're compatible with and not. We have done also tests for measuring moisture in different types of oils as well, and that's a very nice application for these kind of sensors. So they have a very high sensitivity for humidity, and then of course, if there is any cross sensitivity with other liquids, that should of course be screened.
Okay, yeah, understood. So Mark, please.
Yes, thank you. Very nice presentation, Christian. I was wondering, the microstructured fiber you are using, you presented at the very beginning, is it an endlessly single mode one? And if so, are you taking benefit of this endlessly single mode behavior by having a broadband interrogator or something like that?
Yeah, we manufacture our fibers to be endlessly single mode. That means that we can address the C-band and the 850 nanometers in the visible range with the same fiber, basically. The limiting aspect for us seems to be the optical components available. So we normally operate around 800 to 850 nanometers, mostly because that's where we can find most of the components that we need. But as you point out, we could use the fiber for the whole range from 400 to 1500.
Okay, great. Thank you very much.
Evangelos.
Yes, thank you. Christian, I'm wondering, how long can you manufacture these fibers in length?
Well, the manufacturing in length is given by the size of the preform. I mean, we can make manufacturing runs of a few hundred meters to a few kilometers. But the application or the application of these fibers is limited by the loss of the fibers. So the polymers have loss, but also the microstructure might be also a little bit scattering. So for most applications, we're looking at a maximum length of 10 meters.
And so you would connect, say, a 10-meter sample of this polymer fiber with other fibers in order to carry the signal, say, to the analyzer?
Yes, definitely one kind of architecture that we could use, yeah. We also have our contrast system where we've tried to do the approach of saying instead of having a backbone of glass fibers, you would just make the interrogator cheap enough and with radio transmitters, so you can just distribute them in that sense instead.
Thank you.
Ian, yeah, we have several questions also in the chat, but let's go with Ian first.
Hi, Christian. Thanks for the presentation. Enjoyed it a lot. Just a question, like in terms of coupling loss, is that what sort of losses are you experiencing when you're coupling between, say, your photonic crystal fiber and, say, a standard silica fiber? Because obviously, I guess they don't use conventional connectors.
Yeah, no, you're absolutely right. There is a mode mismatch between a standard fiber and the microstructured fiber. So those losses can be between 2 and 3 dB for coupling loss.
Can I jump in here? So would a 3D printed lens on the Fiber-facet be interesting? I mean, that could reduce loss to below 0.5 dB.
Absolutely. It depends on how much of a limiting factor it is for the signal. If you have a strong FPG and you have good laser power on the instrument, you can overcome these losses. So the biggest problem would be for this kind of sensing system is that you don't want to have any reflections from the coupling. That would be the major issue, I think.
So -40, -50 is possible by playing some tricks.
Absolutely, yeah. And then
if you're interested, we can talk afterwards. I can shoot you a mail.
Absolutely.
Yeah. So there is a point of discussion here also. And I think you also already answered the question from Shang-Hu from the CSEM about the losses. Martin from NKT, I don't know if you can make the question live, Martin, because he was asking about the type of light source that you use in the interrogator hardware. Martin is there. Yeah, please.
Absolutely. A pleasure being in this call, actually. And Christian, thank you very much. Yeah, my question is quite simple. What kind of light source are you using in these interrogators, if you're able to tell us? Let's say.
Yeah, sure. So we use SLEDs for our own interrogators. We use SLEDs just to get the spectral density that we need for these kind of sensors. But we have also pushed the technology down to actually using LEDs for our very cheap interrogators with new LEDs. Of course, that means that we do compromise on performance, in particular the speed of measurements.
Thank you very much.
And I connect this question with a question by Joel. He's interested in more details about the interrogator. Joel, I don't know if you can make the question live.
Yeah, thank you. I have curiosity about your interrogator because you mentioned low cost, but what is the wavelength range of operation of the interrogator resolution and things like that?
Yes, so our low-cost interrogator, which is based on an LED, it covers a range from 800 to 850 nanometers, and that's been particularly tailored for our own fibers. Normally we would use SLEDs in that range as well for our own interrogators, and the reason we're working at 800 to 850 is because of the loss of the fiber. At 1550 for our C-band interrogators, we would refer to other manufacturers of interrogators.
Thank you.
We have another question from Asbil Jens Emerick. I don't know, Jens, if you can make your question live. It's about the production of the fibers.
Yes, I'm fairly new to this whole fiber industry, so that's why I was curious to what extent do you actually, what kind of machinery is available for production? If there are some commercial tools, in particular at Shooter, do you use these commercial equipments, or do you also have some in-house development, and how do you monitor then the fiber production process?
Yeah, I can share a little bit on that. Our draw towers are built in-house. There are suppliers of optical components and draw towers, but since we're using polymer fibers and since we had some experience from the university, we decided to build our own draw towers. The monitoring that we have is tension meters for measuring how hard we pull on the fiber and laser diameter measurements for measuring the diameter of the fiber. And other than that, we're just controlling the speeds of the motors and the temperature of the furnace.
Okay, thank you.
We have also a question from Yoshiaki from Sumitomo Electric. Yoshiaki, I don't know if you can make your question live. It's about the accuracy or the difference in the accuracy when you have a sensor in the glass fiber and a sensor in the polymer. I don't know if you can talk about that.
I could talk a bit about that. When it comes to strain sensor, the sensitivity is basically the same because the changes are given by mechanics. So basically, a polymer fiber and a glass fiber, they change the same. For humidity, the sensitivity is about 20 times higher than currently available glass fibers for humidity measurements. And that's because of the large change that the polymer experiences when it absorbs humidity.
Okay.
Yeah, and the temperature is slightly higher for polymer as well, but the range is much more limited compared to glass.
Okay, good. I saw the hand of Shang-Hun. Feel free to raise the hand if you have the question. And finally, it's about the long-term effect of the UV in the polymer fibers. It's by Eric Pinet from Resonetics. Eric, I don't know if you can talk a little bit, or you can connect.
Yes, sir. Actually, my question is more for the long-term effect of the UV, because on polymer, we know that UV will degrade the properties of the polymer. And since you have many aspects in civil engineering, so I was wondering if you have tested this UV effect.
Yes, and thank you for the question. It's a very good question. Yes, polymers, limiting effect of polymers is exposure to UV for sure, for long-term effects. We address this by just shielding the fiber from UV as well as we can. So our concerns have been mostly with regards to other environmental effects. So we have demonstrated, for instance, 5 years survivability in concrete, which is a very harsh environment. But you're right, any outdoor applications, you would need to screen the fiber for.
Thank you, Christian.
And Shang-Hun.
Yeah. Thank you, Christian. A very nice presentation. So my question is about coating and the surface of your microstructure. Do you have any coating?
No. Since the fiber is made of polymer, we don't need to have any coating on it. So there's no reason to strip it or anything like that or recoating. I can though add that since it's made of polymer, it's quite easy to make any other coatings adhere to the fiber. So we have demonstrated also a hydrogen sensor by coating it with palladium. So there's a lot of opportunities for doing extending the sensitivity of the fibers by adding coatings to it.
Thank you.
Good. So thank you very much, Christian, and thank you to all the questions. Yeah, you can feel free to contact Christian for any further discussion or question. And thank you for sharing also your interest in collaborations today. Thank you again. We can move to our next speaker. So we are going to talk about the first use case example in optical fiber sensing in modern wind turbines. So I invite Gonzalo Pereira to share the screen and make your presentation. So Gonzalo.
Hello. Thank you for the invitation.
Thank you for being here.
You can see my screen.
Everything good.
Cool. So we're on the use side of your applications, and I'm delighted by all the technical questions that I couldn't answer about our own technology that I've heard today. So we're more focused on the application, and especially obviously the cost of these and how they're applicable on wind turbines. So a brief explanation why we have wind. A lot of you have backgrounds in physics, but just it's because of the differences in temperatures, right? It's uneven heating of the surface, which generates wind. And then through the use of, in this case, 3 blades, we can convert some of that wind energy into torque, mechanical torque in this case, and then electrical torque to provide electricity to anyone that needs it. There's something called the boundary layer. So you expect higher wind speeds at the top versus low wind speeds at the bottom. This is important not for this side specifically, but a bit later when I show you kind of the data that we pull out of these sensors. In general, we capture the wind using the plates, which we then convert into mechanical torque. We go through a gearbox, which increases the rotational speed, and it goes into a converter and transformer. From that, we produce electricity. Regarding fiber optic applications, we have one related with sensing, which I'll talk about in detail today, but we have two more. So we have the forge. It's the fiber optic rotating joint, which connects the nacelle, so the static part, with the rotating part, the hub in this case. We have spinning blades, right? And we have communications, we have control, we have a lot of information that goes back and forth to the hub and by the nacelle. It goes through the center of the gearbox, right? So it goes through the whole converter assembly. So imagine like a drivetrain of a car. We have to fit a fiber optics through exactly the center of that. So it goes through the other hole to the hub to get that communication and that information going between the two components. The other fiber optics that we have, it's classic application, right? So communications and data transfer. We use edge computing and edge control at these turbines. So we have distributed nodes across the turbine, and they all communicate with each other using fiber optics. Given the amount of data and speed that we request, it's basically the only option to go. So as an industry, if you're not familiar with it, it seems like there isn't a lot of technology going. It's a fairly big industrial machine, but it's no longer an option just to point the turbine at the wind and expect that it produces the best technology, right? So I've put here a simple feedback loop here to understand that sensing is a great part why we can have modern turbines. So we can control the turbine actively, not passively like in the past where we had stall control turbines where the blade itself would stall to prevent it from overspinning. Now we control the turbines using the pitch of each blade. We forecast and monitor ambient conditions. So if we can sense something, we can use predictive control to actually control ahead of time. We can monitor energy production. And the most interesting part that people never think about is we can design innovative products and new control features. For example, we have one of our best known features is called rotor lift control. So we basically take the example of a helicopter and flip it sideways. So basically, helicopter would be something like this, and then we put it in a vertical position. So that enables us to basically use the lift that we get from the blades to remove some of the weight of the natural weight, so the gravity component of the nacelle out of the tower. So every time the turbine is in operation, we generate a lift, and that lift means that we have a lower load on the tower, means that we have thinner towers, less material, lower cost. And we do all of this with the aid of sensors and pitching. So we can reduce the bill of materials cost in many, many ways, in the blades, in the towers, in many components, because we have that sensing capability and that actuation capability. Obviously, all of this is controlled by controller and some smart algorithms. So there's benefits not only for sensing, but also in other aspects of this. I'll focus today on blade load sensing. It's the only one that currently uses fiber optics. And one question might be why, right? So it's located on the blades. So the risk of lightning conduction and lightning is a major issue, and the main reason why we use fiber optics on the blades. We cannot have anything conductive that would basically fry the whole system of the turbine. We also have torque accelerations that use those DCNs, and we have accelerometers, gyroscopes. So it's a distributed system in that case, and we measure a ton of things on the turbine. So each turbine has roughly, I think, close to 1,000 sensors, and all of them produce a lot of data. And we have a fleet of close to 80,000 turbines. So it's a lot of data being generated that we have to monitor and control at the same time. So focusing a bit more on blade loads. Why do we need to measure them, right? So we want to avoid as much as we can that a blade breaks or a tower collapses or we have some form of catastrophic failure. These are machines that are designed to last 20 to 30 years, so it's very expensive to get a crane there to get them replaced, right? It's not a sacrificial component, right? They need to last 20 years. Furthermore, it's something that it's cutting edge in the sense that we're producing structures that are very long, very thin, very light because they're spinning, made of fiberglass and other materials. So, or composite materials in this case. So it's for us really important to measure the health and how many cycles they do and the overall performance of said turbine. And if we observe any degradation from what we expect, then we kind of need to stop it and have it inspected or perform some form of repair if needed. So for example, blade bending is one example here. One of the features, you want to extract as much energy as you can from the wind. So that means that the blade would bend more, right? Because we pitch it differently. We want to put the flap angle as close as we can to extract as much energy. That means also that the blade bends. But it's fine. And again, going back to the plot that I had before of the boundary layer, we have also always wind speeds that are higher on the top, usually higher on the top than on the bottom part. But if the blade is bending here, we have an issue because a bending blade will sever its own tower, will cut its own tower. So one of the applications that we use blade loads and kind of some of the other sensors is to, when the turbine blade passes in front of the tower, we pitch out slightly so it extends, it relaxes the blade, and then we're able to pitch back in again. And we do all of these with the aid of sensors, and blade loads is one of the sensors that we use to do this. So there's a lot of, I would say, clever innovations to try to extract as much energy while keeping in mind the mechanical design limitations. So on the right-hand side, I have a plot of blade loads. It's a 3P component, so 3 phases, right? Because we have a 3-bladed system, right? So if one is observing kind of peak bending, it means that the other 2 are not, and they describe a cycle because we're spinning the turbine. And we usually are able to measure strain, flap, and edge, so kind of taking into account that this is a wing, bending moments, we have axial force, twist, and deflection. And we extract all of this information from 2 sensors. They're exactly the same, so in design, but they're positioned in different places inside of the blade. So the sensor is very simple. We have a laser that shines onto diodes. Sorry, we have a diode that shines onto receivers, and depending on the bending moment locally at the sensor, you can see here on the bottom left that it's glued to the blade. Then we have more light hitting one of the receivers or the other, right? And we can calibrate this. It's a very simple sensor that's covered by an armature to protect it from debris, from there are a lot of things that might happen. Let's imagine a service technician forgets a tool. Then we have a screwdriver flying around the turbine and the sensor is protected. There's a lot of things that can happen. It was produced internally by Vestas, which was then sold to KK Wind Solutions. And we developed this system many, many years ago. And it's a very simple system. That's why we like it, because it's, in our industry, it has to be cheap. It has to be easy to replace if there's an issue. And it has to be, on the software side of things, has to be transparent for us, right? So we need to be able to understand if there's an issue with the signal, with the information that's providing. We don't typically accept any black boxes, right? So we need to be reacting really fast if there's a blade issue, because this generates a stop time on the turbine, and that generates millions. And if we're not able to detect this, then as shown by our competition in this sector, we're going to have blade issues, which creates a lot of problems in the long run, in terms of reputation and sales and all of the above. So this is our largest turbine. I use the Portuguese stadium because we're Portuguese and where we've designed this. So you get the magnitude of this. It's the size of the stadium with the benches. It's not a stadium. It's not a football field, right? It's the football field plus all the standings there. So it's the size of a football stadium when it spins. And for scale, this is our moldings for those blades. And you have a person for scale or a couple of those for scale. Basically, where that person, the first one to the right, is placed, it's usually where we place one of the sensors. The other one is perpendicular to that one. So we capture different moments, kind of the flap moment and the edge moment of the blade. So we capture both bending moments, and if we combine them, we have a way to understand with the two axes kind of the movement of the blade. They're gigantic blades, as you might imagine. These are just a few examples, and we have 3 of these in each turbine. More people for scale. This is trying to go roundabout with a blade this size. So that's why we only try to use this offshore as much as we can. And this is a truck for scale, not a person. In this case, it's a truck for scale. So you kind of see the size of this. With size also comes scale, right? Obvious. And it also means that one of these turbines, if it operates for a year, it can power 17,000 households. So one turbine, 17,000 households. Yeah, it's very big, but has a lot of positives on it. So we're installing fields and have 50, 100 of these turbines offshore. So you start to see the scale of renewable energy that we can pump into the grid. Yeah, that's it.
Thank you very much, Gonzalo.
Anyone has questions?
Yeah, so we are open for questions, so raise your hand. I could perhaps start with a question regarding the sensors, because you mentioned the use of fiber sensors in the blade loads. Do you see potential in the fiber sensing in the other parts of the turbine? I think you mentioned the accelerators use angle as well. Did you use fiber sensors, or do you see potential in the future for them in the other parts of the turbine?
We don't support, we don't advocate for a specific technology. We're technology agnostic, right? We're cost driven. So in our case, we're using accelerometers and gyroscopes because those could be embedded by cents on the dollar on the PCBs that we have existing, right? So if it is a more cost-effective solution that has a bigger lifetime, that generates less visits to a turbine because something has failed or the data is by orders of magnitude substantially better than what we have, then we start to pose the possibility of changing that. But it's at the end of the day, it's bill of materials cost and how hard or how simple, how cheap it is to replace if something fails, or if it doesn't fail at all, it's even better, right? So that is the main driver for us.
Good. And as this kind of meetings is a point of starting collaborations or new developments, is something in particular that Vestas would be interested in discuss, or any kind of collaboration that you are open to discuss with the members or other companies?
I think we're looking into solutions that would be bringing additional features to stuff that we have, right? And as I mentioned, we're also very driven on the data side of things. So it's not only the hardware itself, but also cooperating with suppliers to get that information. So one of the reasons why we haven't changed our system in 20 years, it's because it is very simple, which means that it's very cheap and it's very transparent for us. So if we have an issue on a turbine, we have the know-how, we have the capability to go and do something about it, and the turbine is up and running within a couple hours. And that for us, if you multiply by 60,000 turbines, translates into many multiple millions in what we call liquidated damages. So even in those situations, obviously having a partner is ideal, but it needs to be kind of a transparent thing for us to be able to service it, to get it up and running and then collaborate with those partners to improve the product offering.
Very good. I don't know if there is any other question. You can raise your hand or put it in the chat. Yeah, Peter.
Hello, Gonzalo. Thank you very much for a very nice presentation. It was very informative, and I was really looking amazed on all the details and the parameters there. I'm coming from the company that we are not really a service provider to companies like Vestas, but we are one of the largest manufacturers of the optical fiber components, including sensors, FBG-based technology. We know these products are widely used in the wind industry as well. So I just wanted to a little bit hear your maybe your experience, maybe comparing to the other sensor types you have shown today that have a good and easy use. Whether you yourself, maybe your company, how do you see the potential of the FBG technology for the future of the applications in both blade or maybe rotational elements? Thank you very much.
So it goes back again to the cost, right? So we don't we're very conservative as an industry. We don't want to be early adopters of anything, right? It's a very rough machine in the sense that it needs to last 20, 30 years, right? So we kind of, if we're installing a new technology into a turbine, it's a risk for us, right? So it needs to work 30 years later. And again, cost is the main driver. So if it can be cost competitive with the solutions that we have, then awesome, great. We've seen a lot of competition within this space, not on the fiber optics itself, but for example, cameras. We've seen a lot of suppliers coming up with ideas with cameras. We've seen pilots that would be embedding the fibers on the blade itself, but there's a gigantic issue with that. If there's an issue with the fiber itself, then we're not going to cut away a blade that costs millions to get that. So it needs to be easy to install and remove and replace if needed. So it very much needs to take into account both sides of the economics here. The bill of materials, the reliability aspect of that, and the serviceability and how easy it is to maintain over those 20, 30 years.
Thank you very much. I would appreciate to catch up with you later on some particular topics, not to delay the other meetings. Thank you very much for very, very good answers.
Thank you, Peter. And I think it's the last question. So, Gonzalo, thank you again for being here today, for sharing all your thoughts from the point of view of Vestas. And as I mentioned, feel free to contact Gonzalo also in the chat today for any further discussion. Thank you again. And we can move to our next speaker. So we are going to talk now about slightly different topics. So Center Alpha-Nov is quite well known among other technologies in the laser processes. And they want to share with us the idea of femtosecond laser for laser inscription of fiber Bragg ratings. So Mark, yeah, the floor is yours. Let's see what Alpha-Nov want to propose.
Thank you, Antonio. Hope everything is fine into the presentation. And thanks for the nice introduction. So my name is Marc Castin. I'm the head of the Laser Sources and Components department at Alpha-Nov. And today, definitely we are not specialists in the terms of fiber sensing, but we have a set of competencies that we like to advertise and propose to the community to discuss about maybe potential of new fiber-based sensor application based on specialty optical fiber, femtosecond laser inscription, what could be the merging of these two things. So just to give you an insight, Alpha-Nov is a research technological organization which has been founded in 2007. It's a non-profitable organization. We are roughly 120 employees, mainly localized in Bordeaux area in the southwest of France, with some offices in Limoges. And we're 4 technological departments. So it's the Laser Sources and Components department that I'm heading. Some Photonics system department where their target is to make some integration of complex systems, optical system based on the lasers, and make some custom machines. The laser processing department where their expertise is really what you know, Antonio, about cutting with high precision, drilling, making some in-material modification with femtosecond lasers. But we also have a training department, training centers for making some training and custom training for related to laser and laser technology. So today I will just introduce the competencies of my department, and to give a bit of history. Actually, the basis of my department is really specialty optical fiber interfacing. So based on photonic crystal fibers, we have developed a specific know-how and knowledge on how to interface these very non-standard fibers that Christian gave some examples with his polymer fiber, microstructured one. And based on this knowledge, we moved to mostly to go to some high-end components, fiber-based high-end components based on these specific fibers. And since more than 3 to 4 years, we have also developed some capabilities in terms of femtosecond laser inscription into fibers. We also have some specific expertise in precision gluing and aligning, making us capable to make some new kind of fiber-based components, but fiber-based feature based on micro-optics inside this kind of box. But all this realization, as of today, is really oriented to make some components for laser or custom laser development. And that's why today, with this opportunity to present a bit of our know-how, I would like to try to address the community of the fiber-based sensing to see whether some of these competencies could be used for fiber-based sensing. So I made a selection of 2 topics I would like to highlight a little bit, or expertise in specialty optical fiber interfacing. So when we talk about specialty optical fiber, we are mainly talking about this kind of photonic crystal fiber, and we are addressing the whole zoology of this kind of fiber, meaning the hollow core fiber, some LMA, layer to mode area fiber, which are endlessly single mode. I will come back to it afterwards. Also some very small core diameter fiber, which are aiming at making some nonlinear effects into this fiber, or also some amplification fiber. As you see, all these fiber, we are capable to do many things on that. Some end capping, some adaptation between this kind of very specific fiber to standard fibers for decreasing the losses in coupling and to make it still all fiber. We have capabilities for making taperization or extremity functionalization like green lens, ball lens. And I was thinking that maybe these kind of fibers, the hollow core ones and the endlessly single mode ones, could be of interest for making some fiber-based sensors. Because an hollow core fiber is a fiber in which you are guiding the light into a core which is made of air, but this kind of fiber can be filled with any kind of species, liquid or gas, that we would like to maybe analyze. And it might be of interest for maybe inline monitoring of flow into some industrial applications. And the endlessly single mode fiber are the good point to have the capability to guide light over a broad spectrum, still in a monomode favor, meaning that, for instance, this kind of fiber can guide light from 500 nanometers up to 1.7 micron and 1.8 micron. So if you want to make kind of a sensor which would require different wavelengths for addressing some different sensitivity, these kind of fibers are far better than the regular ones, which have cut off bandwidth of roughly 200 nanometers in single mode behavior. So that's the kind of know-how in terms of interfacing we could propose. And this kind of know-how, we could also join it to some femtosecond laser inscription. So I don't know if everybody in the room is very familiar with that, but the idea here with femtosecond laser inscription is to take benefit of the fact that you are using a femtosecond laser, which has a very high peak power, to focus it into the core of a fiber. And then you can have a very localized modification due to the nonlinear effect, multi-photon absorption effect, which is illustrated in this picture compared with linear absorption in the UV. And so you can have really very precise modification in the core of the fiber. And the good point of that is that you do not need to have any photosensitive agent to UV of the fiber. This means that you can address any kind of material somehow to make this volume modification and to write this refractive index change. So this kind of techniques is already applied because it's compatible to extreme environment if you're taking, for instance, silica glass, and because the kind of FBG you can write inside the fiber will be not too much sensitive to temperature or even radiation, because you can really write into pure materials. So we are in this set of making this kind of components since more than 3 years. We have a couple of stations of different kind, point by point, Talbot or phase mask. So we can do more or less any kind of components like standard FBG, TFBGs, tilted FBG, chirped one, even P-shifted from visible to mid-air. And we can adapt to the material which is required by the application. We also made lots of testing of all fiber fabric cavities. So for all the experts in the room who are used to FBG sensors, I would say we have the capabilities to write these kind of things into any kind of material. But the question is, would it be interesting to merge that with specialty optical fiber that I described below? And the third point is, with this kind of station with a femtosecond laser inscription, you can also write waveguide in bulk materials. And with this kind of waveguides, you can also make some kind of sensors based on evanescent coupling of light. And we have capabilities to make some custom beam shaping so that we can make this fast inscription. We can make low loss waveguides. And we have also capabilities to make fiber coupling of this kind of bulk materials. So I would say we have 3 points here. We have the capability to interface specialty optical fibers. We have capabilities to make some femtosecond laser inscription into these fibers or into regular fibers. And we have capabilities to make some coupling in between the different elements. And my feeling is that based on all these things, we could maybe reach some new kind of generation of fiber-based sensors. And as an illustration, I would like to highlight that with a European project, which is currently under development. This is an European project, which is a FET open one. So it's part of basic science with different universities in Italy, in Hungary, which are making some basic science and kind of theoretical things. But the idea of this project is really to use hollow core fibers, which would be filled by rubidium atomic vapors. And our task in this project at Alphanov is to make the interface of this kind of hollow core fibers with regular fibers, to make some specific FBGs, to make some field enhancement into the hollow core fiber. And the main goal of this is to make new kind of sensors, quantum-based sensors based on these alkali vapor field cells. And for this kind of project, we are technologically working with Glow Photonics, who is providing the hollow core fibers, and the Xlim laboratory, which is in charge of developing a way of filling with atomic vapors these kind of fibers. So this is an illustration for the very high end, talking about quantum sensing. But I'm pretty sure that by merging all these competencies we do have regarding the specialty optical fiber technology and the femtosecond laser inscription, we might be able to address maybe some new kind of fiber-based sensors. And that's really the kind of competencies I would like to advertise today, so that if you have problems, or to submit to us, where we could maybe think about potentialities of new components. And this is just talking about our core competencies in terms of components, but we have also capabilities to develop some lasers for making interrogators or specific interrogators. And at the scale of Alphanov, we also have this photonic system department, which could be also in support for making a new kind of interrogators. So yes, today the idea is really to demonstrate what we're capable of, and so that we can really have exchange about your problems and maybe solutions we could bring with our competencies regarding specialty optical fiber and femtosecond laser inscription. Prior leaving the floor, I would like to make a quick advertisement for a quantum sensing event, which will be held in the frame of the CRISCube project. It will be held in June in Limoges, and it's an opportunity also to discuss about maybe potential applications of this kind of quantum sensors, but also a potential application of this kind of technology for sensing in a more larger way. So it was short, and the idea is really to be eager to learn about your sensing problems and to see whether we can support you in some developments.
Thank you, Mark. So we have time for questions or comments. I would perhaps start with a question about the platform.
Yeah.
Thinking in the diversity of fibers, also the different characteristics that the Bragg ratings can have. I guess the platform for inscribing the gratings needs to be flexible. Is something that you also see from this side, or do you want to go in more, let's say, more fixed situation where you address some particular cases?
Now, as an RTO, our target is to have flexible platforms so that we can really try to address some very custom needs. So the way we have to inscribe is we do have platform for making point-by-point or plane-by-plane inscription, meaning that we have no non-recurrent engineering like phase mask to provide. We can really write on the fly with periodicities, with modulation depths that we can adapt. And the idea is really to have an agile platform to be able to propose some agile method for optimizing maybe sensors or at least components.
Mm-hmm. I don't know if there is any other question or comment. Yeah, Roman.
Yeah, thank you for the presentation. I have rather a technical question. I'm curious to know about the lateral resolution of your femtosecond laser inscription. As far as I understood, this is a non-linear process, so it should be better than diffraction limits.
I would say yes and no, because it's nonlinear effect. So indeed, even if you have a Gaussian beam, just part of the Gaussian part will trigger the nonlinear effect. So you can go to I would say maybe 80% of your wavelengths in terms of resolution, because you are not hitting too hard the fiber. Because you want to make some smooth, at least in the case of fiber laser components, we are trying to make some smooth modifications, which might be a bit different if we want to go onto some sensing applications. So as of today, we have illumination capabilities down to 15 nanometers. But on the longer term, we are planning to maybe make some custom laser development in my department to be able to illuminate close by the 400 nanometers wavelengths, which is still capable to inscribe through coatings, because that's one of the magic of this capabilities, that you do not have to remove the coating of the fiber to make the inscription, and so to try to gain in terms of resolution.
Yeah, very interesting. Thank you.
Yeah, Young. You're muted, Young. You're muted, Young. You need to unmute the bottom left.
Yes. Now, can you hear me?
Yeah.
Yes. Okay. Thank you for the very nice presentation. I have one question according to the pi-shifted FPG. Do you inscribe the pi-shifted FPG by point by point or face mask?
As of today, we made some lots of testing in point by point. It's still possible to make it in a phase mask, but the non-recurrent engineering cost for a phase mask P-shifted is quite important. So I would say if we had to develop some specific solution, we would first move maybe to point by point to make it agile and find the good parameters. And if we had to move to serial production, or at least small volume production, where we can really take benefit of the stability of the phase mask method in terms of reproducibility, we could move afterwards to the phase mask. But it's really depending on the performances of your phase shift you will request.
Okay, which means you can inscribe FEG with both method. Which one is more stable, or maybe the phase mask one?
I would say if I had to go to a large production and the phase mask technique allows it, because you don't want to have hundreds of millimeters long P-shifted, but something which is more reasonable, I would move to the phase mask for large volume quantities for the reproducibility. But for developing, I would say the point by point, plane by plane inscription would be more agile.
Okay. So one more question: how can you use point by point method to inscribe a pi-shifted phase FEG, which means you inscribe 2 FEG at one time, or
we have specific ways of synchronization, which allows us to have a perfect control of the P shift.
Okay, sure. Thank you.
Welcome.
Yeah. You're muted, Ian.
Thanks, Mark. Thanks for the presentation. Just a question. Have you looked at the high temperature sensing possibilities of these femtosecond gratings? And in that case, do you have any idea of what sort of temperature ranges these could accommodate?
So I'm not a full expert, and as mentioned, first we went into this kind of technology for manufacturing components for lasers. But as far as I know, and maybe I will say some bullshit, but up to 600 degrees it should be okay. Maybe more. It really depends on the laser matter interaction you're gonna use to inscribe. If you make inscription with a standard UV process, we call that a type 1 inscription, which will be very sensitive to temperature and can be erased by the temperature. But if you use femtosecond laser inscription, you can trigger some other effects, which is named a type 2 inscription, which is much more making a structural change in the matter, which allows to go to very higher temperature, but the FBG will have more losses. So it's a trade-off in between up to which temperature you want to have your sensor working and which kind of losses you can accommodate onto your interrogation line.
Thank you.
So I think there is no more questions. So thank you again, Mark. Thank you for your time today, and feel free to contact him to discuss any of your ideas for the fabrication of gratings.
Thank you very much.
And we can move to our next speaker. So we have another manufacturer of fiber Bragg sensing solutions, Proximium, and it's a pleasure to have Christer Preudt, the head of R&D, to talk about the industrial solutions in this technology. The floor is yours.
Okay, hello everyone.
Now we hear you very good, so thank you for the improving.
I found the button. Anyway, welcome everyone. I am very pleased I'm allowed to have a short presentation here. And my colleague Gunnar Hedin presented more of the basic technology, so I thought that it was more interested to tell you a little about what examples we have, where we're using our fiber Bragg racing and our systems. Very short about Proximium. So we at least say we are world leader in production of advanced fiber Bragg ratings, and we started with telecom. So that there you need very high quality of the gratings. And then we started with sensor about 10 years ago. We've been in the business for almost 30 years. So I would say we're not a startup anymore. We have quite good facilities with 2,000 square meters of clean room. You see the nice building here to the left. And we use a specific unique way to write the fiber Bragg gratings. We are not using any face mask, so we don't have any of those problems. So one of our specialties is to manufacture very long, continuous short gratings without any phase errors. So we make them up to 20 meters. They are very useful in telecom. They can also be used for sensing, but in most cases, we use discrete sensors for discrete gratings for sensing, but we of course make multiple of them in the same fiber. So we have delivered a lot of fiber Bragg gratings. We are also a fully owned subsidiary of the Hexatronic Group, which is a quite big company. So that gives us I mean, because in many cases, if you're a supplier, you need to be a long-term supplier. So that's good thing. And we are situated in Sweden, here in Kista. I'm sitting in the office. And so I guess that gives somewhere about 30 people in the company. So very short, this is a fantastic illustration, just to give an idea of what the system is for us. So we make the sensor gratings, but in our fiber, in our own facility here, so we have our own developed machines. But then also we need to put it in some package that's suitable for the application. We need to supply cabling that works in many times quite tough environment. And then we need an interrogator. This one is also developed by us. And finally, and that's not the least. We need to make out software to present the data to the customer interface to other system. So it's and we are quite vertically integrated as a supplier. And in some cases, we only deliver fibers with sensors on it. In other cases, we deliver a complete system. Our experience is that in an industrial environment, the customers they are most interested in this case get temperatures. And of course, they say it's fancy with fiber optics, but in the end, they don't care too much about the technology. So we supply a solution where we optimize the fiber gratings to the interrogator, and then of course have some software that interfaces well with the customer system. And depending on the application, you could have quite different requirement on the interrogator. So we also source other interrogators. So if someone has an interrogator to sell to us, we are interested. And also tunable lasers are of interest. So one example here is we spend a lot of time on is to develop sensors for airborne applications. This is one thing is to develop the technology. Another thing is to really get it certified for use in an aircraft. And a common problem in most aircraft is that you have a bleed air system for supplying power for the de-icing and for air conditioning in the airplane. And so it's a power source that you take from the jet engines, from the compressor stage. But as you have a lot of moving joints and so on, you are a bit afraid that you should get a leak. So you typically have a bleed air overheat detection system. And now we have a supplying this as a fiber optic solutions. And there's plenty of this piping inside the plane. So and you want to monitor it almost everywhere. So that means you need to supply like 6,000 sensor points that is distributed over 70 meters. So we need to make a lot of gratings. And also important here is that we cannot supply individual calibration with each fiber cable we supply. They need to be identical in wavelength. So that's also quite I would say a challenge, but we have been able to meet that. So we manufacture and we also developed these sensor gratings. And we also helped our customer with the design of the optical part of the interrogator. So we also try to be a good supplier in that way to also supply some knowledge. Second application where we have a lot of customers is in continuous steel casting. I guess most of you don't know too much about continuous steel casting, but that's the dominated way of casting steel. And this is like in huge steel plants, where you, here in the case, this is from an example from in Sweden, where you have 180 tons of liquid steel coming in, and then you allow that to flow into first the tunders and then here into the mold. You see my arrow, hope. And these are 4 copper plates that are cooled with a lot of water, and then you will have the steel that will be will not what's that? It will get solidify here, at least at the surface, with the rate the steel is come out with the rate of 1 to 3 meters per minute, and then it goes down here, and it's like this is maybe 200 millimeters width here, and then it's in the depth direction, maybe it's up to 2 meters. So this is big, but important here is a critical stage here is the solidification, because that can affect the quality, and if you're unlucky also you can get that you get a stuck here of the surface of the steel, and then you can get a breakout where you have steel flowing all over here, and that ends up with quite expensive, because it's a bit tricky to remove solidified steel over all these rollers and equipment here. So that's important to keep track of the temperature in these copper plates. So, and that you usually use to do by thermocouples, but they are where you can have very limited number of thermocouples, maybe 16 on the mold plate. But we instead have fiber that are vertical, mounted into drilled holes in the copper plate, and each sensor then could have maybe 50 to 75 individual sensor points. So and then you have this on all the plates in most cases. So and we also have did the first installation in 2014. So this is quite mature now. And in that case, we have 2,660 sensors. So you get like a thermal map here on the display. And of course, the logical practical thing to have these cables that should withstand tough environment. And we also need a very reliable interrogator here that should be working for a long time without any problems. So just this is an example of a real copper plate. So this is maybe, I guess, 800 millimeters high or something similar to that. And you also see the optical cabling here. It's quite tough. And also you have expanded beam connectors here, because these are handled by the operators in the steel plant. So they, it's not, you should be able to handle the dust environment and people that are a bit rough with the equipment, but it works very well, actually. This is just an example here of what you can see from using. So you see this thermal map here. It's about 220 degrees Celsius here, and you see so that now this is accelerated in time. But you see that you have problems here when the solidification moves around, and this could be a case where you could have like breakout, for instance. And also, you think steel is one thing, but there are so many different steel grades, and some are very difficult to cast. So there's a very big interest here, because if you just can improve the quality a little in the casting, that's the most critical stage. That's really worth a lot for the plant. And this case, it was Tata Steel in the Netherlands. So just what you can find, you can see this temperature variation, and you also see that if you change the casting speed, you can also see how that affects the solidification by monitoring temperature. Very important is the mold powder you put in on top as a lubricant during the casting, and the effect on the temperature. And a common problem is that you get cracks on the surface, and that are quite expensive to remove. And even worse, it might, if you have hot rolling on this, and then you can end up as defects on the final product. And you also use, in many cases, you use an electromagnetic brake or electromagnetic stirrer, and they, of course, will affect an electric sensor. So this is good that you can monitor the system while the brake and stirrer is on. That was not possible if you have like a thermocouple. So there's actually still a lot of work going on how to use this data in the best way, but there's a lot of interest because suddenly they can see what's happening inside the mod. So in general, with the fiber guides, you can do more optimization, and we also add safety because you can detect these breakouts. And in the end, you want to reduce the cost and energy use because you don't have to redo what you say, remelt when it's really goes bad. And also it turns out that this is really robust and reliable. That's very important in the industry. So this was all from me, and thank you for your attention.
Thank you, Christer. We already have a question, Xianhun.
Yeah, thank you so much. Very nice result. So my question is about your interrogator. So it seems like your FBG is every 1 centimeter. So every 1 centimeter you have like a pointer sensor.
Actually, they are not equally spaced. So you're down to like every touch point every 5 millimeter. Typically, you want them dense at some points at the.
Yeah, and you're saying all the FBG are in the same frequency, same wavelength?
No.
They are different. Okay. Okay, and then your interrogator is CW based. It's not pulse based.
No. In that for the steel, it's a CW.
CW case. Wow. Okay, and so you are writing the grating while like drawing your fiber.
No, we are buying like different sort of fiber, and then we inscript it with the UV laser.
Okay, thank you.
Thank you, Xianhun. Any other question for Christer? Yeah, Matt from Eblana. You're muted, Matt.
Hello, Christer.
Okay.
Very interesting. Thank you very much. You mentioned that you were interested in tunable lasers. Can you describe more about what kind of things you'd be interested in?
Yeah, in general, a tunable laser is of course a good. There are like two ways to do for an interrogator, and a tunable laser is great in many aspects, and in the end you can think of fast swept lasers for application with high time resolution, or you can think of with more slower but with very controlled wavelength and so on. So of course it's good if you have a tunable laser that in some way is either continuous tuning or that you have good control over like where it has. So it's I would say in many cases the cost of the interrogator can be the problem if for someone to install a fiber optic system, especially because it's an upfront cost. So it's always a good interrogator can enable new function, but we also see for different applications you have very different requirements. So it's more what you can. We see what as is available, and then for each application we are try to get the best system solution for the customer, and also typically we also optimize our sensor, our gratings for the sensors so they fit the integrator.
But are you looking for things with tunability of like a couple of nanometers or like tens of nanometers?
Yeah, with fiber Bragg rating, I would say a large tuning range is of course a big advantage.
Thanks.
Thank you very much. Any other question for Christer? I have perhaps a general question for you. Is in these industrial applications, from your point of view, what is the challenge nowadays? Is the selection of materials that be sustainable in these harsh environments is already discussed and it's clear what you need to use, and is to focus in the parameters that you need to check, or is also how to create something that is durable in the time?
I would say durability. I don't think as in the end it's a packaging solution. So I think we're able to address a very long-term reliability, and we also we have solution for up to 600 degrees Celsius high temperature sensor. So I think that's solved. But in the end, it's that they are so different. Each requirement is quite unique in that you need a special solution for that, with like from everything from sensor design to software. So it's more, and in some cases, fiber optics maybe not the best solutions, but I think it's quite mature from our point of view.
Okay. Good. Thank you very much, Christer. So I don't see any other question. So thank you again for the presentation today and for being here. And we can move to our next speaker. So I met Evangelos a couple of years ago in the great meeting we had in Porto, again about the topic in fiber sensing. So it's a pleasure to have him again today online to talk about their strain monitoring of Stator coils with optical fiber sensor. So Evangelos, nice to see you again. And yeah, the floor is yours.
Thank you so much for the opportunity to present this development that we have conducted at Siemens. I've heard a lot of fiber Bragg grading talks here today. I just want to show you here on our typical turbo generator some of these locations where we put fiber optic sensors, and most of these locations have been utilizing fiber Bragg gratings. But today I'm going to talk about a different sensing technique that does not use fiber Bragg gratings. It uses white light interferometry. The choice for fiber optics within our turbo generators I think is probably the best choice. And the reason for that is you need an all dielectric material because of the extremely high electromagnetic fields that are generated inside the generator, the high voltages and the high currents, etc. And so using fiber optic sensors into our generators for Siemens Energy, at least, has been since the mid-1980s. And we've progressed and used different technologies that have been developed within optical fiber sensors. And so the issue that we really have in the industry is that it has been extremely slow to adopt using optical fiber sensors, although we've been a number of decades that have utilized these sensors. And yet the industry is still very slow into adopting these as a viable commercial product. I can say that currently our most successful commercial product is the vibration monitoring that, in fact, that's the one that started back in the mid-1980s using optical fibers. I think it was one of the first usages of optical fibers to monitor inside the generators. And this product we call the FOVM, fiber optic vibration monitor. We utilize this on a lot of our generators, especially the very big generators above 800 megawatts or so, and certainly on the nuclear units too. Some of these points here that we do the measurement, as you can see, most of the points are internal to the generator. That's why fiber optic sensors are ideal for that. Although there are some locations on the outside, the gussets, we instrument those with fiber Bragg gratings, multiple fiber Bragg gratings, so that we can properly adjust the weight of the generator depending on the location, the physical location of the generator, so that we can properly align the generator to avoid any imbalances when the unit is in operation. So the technology that I'm talking about today is the white light interferometry. And the way that these type of sensors are manufactured, they essentially put two reflective mirrors, as we call them, within the core of the optical fiber. And the two mirrors are separated by a known distance. And light that is propagating down the core of the optical fiber encounters the first mirror. Part of that light is reflected from that first mirror. The rest of the light is transmitted through that mirror, and then it interacts with the second mirror a distance away, and then that light is reflected off of the second mirror. And so the light from mirror number 1 and the light from mirror number 2, they recombine at the detector, and it forms an interferogram. It forms an interference pattern. And so that is the basic construction of the sensor. And so by reading the number of fringes, so to speak, we can accurately measure the amount of stretching that Fabry-Perot etalon has undergone. And that gives us an extremely precise measurement of the strain of the substrate that the sensor is bonded to. So let's, here we go. I'm assuming that everybody can see the presentation. On my screen, I have, maybe I have the, let me just first ask, everybody can see the left and the right side of this image that I have here. So yeah, thank you. So as I mentioned, as the substrate experiences a stretching, the two reflective mirrors, they also experience the same stretching, and so the interferogram moves in position, and by counting the number of fringes, we essentially have a direct measurement of the amount of stretching that is undergone. And of course, you know, from simple measurements of the definition of the strain, we get the amount of strain that the substrate has encountered. So I wanted to show you the location where this particular sensor has been deployed. I have here a number of photographs of, this is what we call an in-field rewind. And so what we do is we remove the rotor from the generator. And then you can see here on the left-hand side, you can see, we call these the teeth of the stator. And then within the teeth, we wind the generator. So we put in the physical windings, the copper windings where the current is generated from the rotation of the rotor. And so you can see for this particular generator, I believe this was an 800 megawatt generator, the diameter of the core of the stator core is roughly, it's almost 6 feet. And here on the middle picture, you can see here's a winding. Here's one winding. It takes 4 people to physically bring it into the stator, so that we will wind from one end of the stator in the bag to the front end of the stator here. And then we will repeat that. So we have 2 coils, a top coil and the bottom coil. What's important is that there are no cavities, and there are no areas where there can be any type of discharge, electrical discharge between the coils and the stator. That could lead to catastrophic failures of the machine. And so how do you measure that? How do you monitor, you know, how well, you know, the coils are fit within those teeth of the stator? And so we have, within the industry, we have an idea of what the tightness should be for those 2 coils. And what we wanted to do was we wanted to be able to measure the amount of tightness that those coils are under. So if you have a measurement at the beginning, whenever the generator is rewound, and then you monitor that amount of tightness as the generator progresses in its lifetime, in its age, you get an idea of whether or not you're experiencing any looseness within those coils. And in the past, this has typically done on a time basis. So it was never based on the condition of the machine. It was based on just a set period where we would have to go in there and physically measure the tightness of those coils. Bringing down a generator and removing the rotor so that you can make those measurements is very, very costly, not only to to the service personnel of Siemens, but it's extremely costly to the operators of the generator. And if you have a very large generator, in this case 800 megawatts or greater, it could be on the order of $1 million a day of lost revenue while that generator is offline. And so instead of having a time series based maintenance schedule, the idea here is, well, let's keep an online measurement of what the tightness is. And so now we have a better indication of the condition of the machine, and we can better plan for those type of outages that that necessitate us going in and either retightening or rewinding the generator. And so I want to show you our own shop test that we conducted when we were first looking into the viability of this particular technology. And this is located in our Pittsburgh service center. And you can see on the right-hand side, you can see the rotor of this generator. It has been removed so we can have access to the windings and to the slots. There we call them. I was given access to 5 slots to install 5 of these sensors at various locations so we can determine their viability. I believe that this not a very big generator. This is probably a medium-sized generator here. I believe the diameter here is on the order of perhaps 1.5 meters or something like that. So here are the 5 slots, as we call them, that I was given access to install the sensors. I was given access to slots number 22 through 28 or 27. Yeah, there for the 5 sensors. What's really important in deploying any type of sensor with in any field is, yes, we want the sensor to last a very long time during the operation. But a very key critical aspect is the installation of the sensor. And in our industry, our installers are used to these very large machines that have a lot of weight associated to them. So to be gentle with the optical fiber sensors that most of us have experienced when we first use these type of sensors, it's not practical. So the sensor needs to be robust in not only in its workability during its lifetime, but also during installation. And here you can see how the installation for the shop test went about. You can see we use hammers and very stout gentlemen that are not afraid to do whatever they need to do to get the job done and finish as quickly as possible. So this is something that we keep in mind for any type of sensor that we install, or particularly to fiber optic sensors. The middle picture here shows the installation of one of the sensors. I believe it was the top sensor, the first sensor, number 1, and it's you can see the black lead fiber cable that comes from the actual sensor itself. We route these outside. This particular generator was an air-cooled generator, so there was no need for any type of pressure seal to go through a penetration. But a lot of the big generators, they are hydrogen cooled, so it's very important that not only do you have the proper sensor that can function in a hydrogen atmosphere, but also the proper components that will allow the penetration of that hydrogen barrier. And so let me just briefly talk about the benefits of this particular technology and in fiber optics into our generators. So for stator winding tightness tests, they're typically conducted every 4 to 6 years, I had mentioned. With monitoring, these tests can be considered on as needed basis. So if we know the condition of the machine, we call this condition-based maintenance. If we know that an outage needs to be scheduled, material can be ordered prior to the outage and have everything ready on site so we can minimize the amount of time it takes to bring the machine down and then bring the machine back up to operation. We, of course, we can postpone the normal test that we would do according to the time schedule, and perform these tests as needed. Of course, fiber optics, being an all dielectric components, are extremely important, especially measuring these measurands inside to the generator, because they're impervious to electromagnetic interferences. For this particular sensor technology, it is an absolute strain measurement, and it is not affected by temperature as your typical fiber Bragg ratings. Of course, we know the Bragg condition is twice the effective index and the pitch of the grating. So by measuring the difference in the pitch of the grating, we have a change in the Bragg condition, in the Bragg wavelength. But the effective index is something that is an order of magnitude stronger in a Bragg rating, and the effective index is a function of the temperature. So we eliminate the need to also have a temperature measurement at the sensing location, so that we can accurately measure what that absolute strain is. Of course, these fiber optic sensors are intrinsically safe, but with the white light source, we avoid using a laser source, which in our industry means that we do not have any ATEX concerns. ATEX is acronym for the atmosphere explosive, which means that if you make a penetration into a hydrogen atmosphere or any atmosphere that can be ignited, then you have to take into account what the ATEX conditions are for the amount of laser power that is being transmitted through the penetration. For white light interferometry, that is not applicable. And of course, the measurement is independent of the light intensity and any light losses in the optical train, because we're measuring the fringes. In other words, we're counting essentially the number of fringes as that interferometric pattern shifts. And so we do not have to take into account, as compared to intensity measurements, fiber optic sensors that use intensity measurements as their measurement. And of course, the other big point is that interferometric measurements are very sensitive, so we can have extreme resolution in the amount of strain that is being experienced because of the interferometric aspect of the measurement. And I believe that, yes, our lawyer's company disclaimer. Thank you all for your attention.
Thank you, Evangelos. So we have time for questions for Evangelos. I have perhaps one first question about the fiber, because we heard in the previous talks also about the use of specialty optical fibers. Is there something special in this sensor, or perhaps you are considering to use in the future specialty optical fibers for any reason?
2 points in answering that question. I am constantly looking for different ways to make measurements, not only within our generators, but also in our gas turbines and or any of the other machines that we use within our industry. So although my background is in fiber Bragg ratings, my first love, it does not hinder me from assessing and looking at other technologies. To the second point of your question, the optical fiber that we use for this particular technology there's nothing special about it at all. It has to be multimode fiber because we're pumping white light through the optical path.
Okay, very good. Sahum.
So actually, my question was about distributed fiber sensing, but since you are using multimode fiber, probably a distributed optical fiber sensing system is not suitable for.
It is not possible with this type of technology to have multiple sensors on the on one optical fiber.
But somehow distributed sensing fiber can localize your temperature and strain at any position of interest. It's like Brillouin based or Rayleigh based.
Yes, those are other technologies we've considered for other applications within the generator. But in this particular case, for the monitoring that we wanted to do on the coils within the stator, this proved to be the best that we down selected.
Okay, thank you.
Yeah.
I have a final question about the source, because you mentioned laser
Mhm.
can be useful due to the ATEX regulations.
Mhm.
Kind of diode that you are using is a white lamp using a bulb, traditional lamp.
Yes, thank you. I do not recall off the top of my head the type of light source. I do not believe it's an LED source. I believe it's if you wish, I can take this offline and
Okay.
tell you what
Yes.
type, but it's a standard.
Yep.
Yeah, it's a white light source.
Okay, very good.
Yeah. Mhm.
So if there is, oh yeah, Christian, please.
Hi, Angel. So thank you for a very nice presentation.
Thank you.
I was just wondering, just to understand the application size or the market size, you might say, for this application. Does this apply to all generators, or is it just for the big ones, you might say, or could it go down to the very small ones as well?
Oh, no. We could, I mean, this can be deployed in any size generator. I do not see the limitation. The reason that I say this would be for big generators is, as one of the other presenters had said here before, cost is the fundamental driver. It is the number 1, 2, and 3 reason of all drivers for this. So with the larger generators, because if there is an issue, especially a failure, or if the generator has to come down and be repaired, it is so costly for the customer that it is extremely important for them to have these type of monitoring systems, whether it be at vibration or strain monitor, etc. So the driver for our customers, when it comes to installing these type of systems, our customers that have very large generators, to them, it makes financial sense to do this. For the customers that have the smaller generators, and smaller, I mean on the order of 300 megawatts, or say somewhere between 200 and 500 or 600 megawatts would be our mid-sized generators. Typically, those customers would prefer that, well, we don't really want to have a very fancy schmancy system in here. We're happy with the old way of doing this. Every 4 or 6 years, we're going to have the inspection. We've done it for the past 150 years. We're going to keep doing it. So plus it also depends on the customer too. Unlike, for example, the auto industry, where they sell millions of units every year, in our industry, we do not sell millions of generators every year, right? It's on the order of many dozens or so.
So it's fair to say that the demand is there for monitoring, even for the smaller ones, but there's a barrier with cost and installation.
Of course, and just like it is in any other industry. That's absolutely right. And maybe I wanted to mention this. I didn't put it on the slide, but a typical strain gauge, even though it is very inexpensive, a typical strain gauge has 4 wires, and the fiber optic sensor has 1. And so there's another. I mean, if you were to install 10 of these sensors, which is not a lot, if you install 10 of these sensors, you have 10 fiber optics, or you're going to have 40 of these wires that have to be routed outside the generator. So yes, the normal regular strain gauges may be much less expensive than the fiber optic ones. You have to consider the entire aspect of installing the strain gauges, right? So it's, as I mentioned at the beginning, it's difficult getting the customers within the power industry to adopt these, but it's coming along. It's coming along.
Thank you very much for your insight.
Mm-hmm.
Robert.
Oh, thank you very much for the nice talk. I try to keep it short. Do you have any idea how much power in terms of power density you want to launch into one fiber?
That is a standard that is prescribed by the CE, ATEX, and I don't recall off the top of my head, but that is something that is readily available from the public sources.
Okay, nice. Thanks a
Yeah.
lot. Maybe
Yes,
just to
sure.
follow up, you said you want to have a white light, right? A broadband source coupled into your fiber. Is it ever a challenge for you to couple equally well all the spectral range, or is it something you don't really have to care of because you have sufficient power?
It is for this type of measurement, it is irrelevant what the spectral range is, because what we imagine a particular wave packet within a spectral full width half max, let's say. What we're interested in is the reflection of the two mirrors in the Fabry-Perot etalon. And so, I mean, if we're using a light source that is, of course, it has to be matched to the detector, but that goes to the manufacturer of the analyzer of the monitoring of the monitor per se. So it doesn't. I don't think that it matters what spectral range we're using, whether we use a xenon arc lamp or any other type of arc lamp. The important aspect is to be able to detect that interference pattern.
Okay, all right. Thanks.
A final question, Joel.
I have curiosity about the vibration sensor. What is the range you are interested in?
The vibration sensor is based on a fiber Bragg grating technology. As I mentioned, it is one of our longest running examples of fiber Bragg grating. I mean, commercially we have been installing these since 2010, so this will be our 16th year of using fiber Bragg gratings into the vibration. But you can imagine these machines are very, very large and very heavy, and so the dynamic range that we're looking for the vibration sensor is on the order is less than I would say less than 1500 hertz, right? I mean, these machines operate here in the US, they operate at 60 hertz, and we're interested in twice line frequency, which would be 120 hertz. That is the fundamental driver of our generators. Of course, in Europe, it would be at 100 hertz. So as far as dynamic range is concerned for the vibration sensor, you know, it's acceptable for it to be, say, up to 500 hertz, 1000 hertz even. What's more important for us is the resolution that we get, and being able to make that determination for those particular sensors.
Good. So thank you again, Evangelos. Thank you very much for the great presentation and for all the answers to the questions. And we can move to our next speaker. So I mentioned already that we have Keystone Photonics that they are proposing. We talk about fiber gratings, interferometry as well. And now we are going to talk about using micro-optics attached to the fiber as a solution for sensing applications. So Roman Sapkeski is the Senior Customer Solutions Engineer at Keystone Photonics. So Roman, the floor is yours.
Yes. Thank you, Antonio, for the kind introduction. And thank you for providing us a platform to speak about not really classical solutions to fiber sensing. I will share my screen in a minute. Do you see my screen?
We see the screen now in full mode. Perfect.
Thank you. Yeah, I would like to start with the definition and with emphasizement of classic fiber sensor. So here we detect reflection or transmission shift due to changes in transmission in temperature or strain. So this is represented by fist hitting a fiber here. So typically we use fiber Bragg gratings. So in other words, we use classic fiber sensor and use fiber intrinsically as a sensing device. But here at Keystone Photonics, what we do is we produce a fiber probes. So instead of using fiber themselves, we use end of fiber, so fiber tips. So we use additive technology of 3D laser printing. Basically, we also use femtosecond lasers, but instead of inscription, such as Alphanov company does, we do additive manufacturing of polymer lenses. And we do not really attach fiber lenses, but we fabricate in situ. So we really detect cores of fibers and fabricate polymer micro-optics in situ and use them as sensing devices. So this is more illustrative example of our approach, of Keystone approach. Here you can see two typical structures printed by Keystone Photonics. So this is a cross section of a fiber array, and first structure represents freeform structure. So this is a globe, and the second fiber was used for printing a periscope lens that focuses light into this globe. And basically what we can produce at Keystone Photonics is any kind of freeform optics. So we now focus on refractive optics. We produce different micro lenses with reproducible beam shapes and beam expanders. And this is not really a marketing image. What we can do is really focus light into Karlsruhe, Germany, where Keystone Photonics is situated. So we are fast growing startup. There are around 10 people in it. And yeah, so speaking about industrial applications, we provide innovative solutions for optical coupling, and based market is wafer level testing. So here you can see two typical products. So we fabricate lenses on fiber arrays for both grating couplers solutions and for trench coupling, where we can deflect light by 90 degrees or by any artificial angle. We can also fabricate beam expanders, and we can produce mode field diameters starting from 2 microns up to 15 microns of mode field diameter. If we compare our technology with conventional technology for wafer level testing and for optical coupling, I want to emphasize these graphs. So this is coupling efficiency versus positional misalignment, and the red curve represents variation of coupling efficiency using Keystone lensed fiber probes, and gray curve is just bare fiber arrays, where when you move the bare fiber array as close as possible to the wafer. And as you can see, so using just normal technology, you are prone to variation in coupling efficiency, and our printed lenses have much better coupling efficiency and less prone to variation. And this is for grating coupling approach. For edge coupling, our solution is basically the only one, because the only possible alternative to edge coupling is using a 45-degree polished fiber array. And here you need to move as close as possible the fiber array to your edge, to the waveguide, and using our approach, we can achieve up to 1 decibels of coupling efficiency, and using the standard approach, you will achieve something like 4 dB, with very large variation. And if you want to improve coupling efficiency using the standard approach, you basically crash the fiber array into trench. So our solution provides very efficient method of optical coupling using trenches and edge coupling. So we are currently dominating the market for lensed fibers. We are collaborating with many major players in wafer level testing area. So we provide our lens fibers to Form Factor, to Ficontact, to MPI testers, and to many other photonic companies in the photonic industry. But since this meeting about fiber sensors, I'd like to introduce also a real optical distance sensor. So this is our latest development. Here we actually, the idea of this distance sensor was born when we faced the challenge in wafer level testing first. So here you need to understand the distance between fiber and your chip. And basically what people typically use in this area is they use an extra capacitive sensor or additional distance sensing device, which is very difficult to align. It costs money and yeah, it's simply ineffective. So we decided to kind of build a solution for optical distance sensing. So this is just a lens printed on a fiber array, and using a confocal principle, we can scan the lens, scan the fiber array, or just a bare fiber, along the z-axis, so up and down here, and we can measure back reflectance or back coupling efficiency. And this is the graph, the example of this kind of measurement. And here, if you achieve the point of best coupling, you achieve the distance when the distance between lens and your fiber, distance between distance between the lens and the chip equals to working distance of the lens. So, meaning that we can calibrate this distance and calculate distance without using any extra capacitive or external sensors, which is very promising approach, first of all in wafer level testing, but we also believe that this approach can be used in different areas. Also, just to one comment, referring to the previous speaker, so here we can also create a Fabry-Perot cavity between the lens and the chip. So here you can also see the interference patterns that caused by Fabry-Perot cavity. So in this case, this is rather noise than a helpful feature, but we currently studying it in more detail. So what can we offer is 3D printed micro-optics based on your design. So we provide solutions for fiber arrays up to 64 channels. We also work with different wavelengths, starting from visible light up to 2 and plus microns of wavelength. We directly print them on fiber arrays, and what we're looking for is, so we do not really want to limit ourselves to wafer level testing, but we currently looking for new applications. So for example, we can also print lenses on fiber Bragg gratings as well and use them for some kind of spectroscopy. Or we can also study viruses and so on. So if you have any ideas on how we can enhance or how can we be helpful in your application and with our 3D printed micro-optics attached to Fiber-facets, please reach us out and or just write to us, and so I'm happy to answer questions. Thank you.
Thank you very much, Roman. We have again time for questions. Christian, please.
Hey, Roman, thank you very much for that presentation. It's very interesting technology. I was just wondering, how scalable is it? I mean, is it really process heavy, or can you spew out millions of this in the future? And the second question is also, are you limited to the end facet, or could you do this on the side of the fiber as well?
Yeah, thank you for the question. So regarding scaling, so we use 3D laser printers from Vanguard Automation, and currently the printing time of one lens, so depending on the design, so it takes around from several minutes to several hours. So depending on the amount of machines, yeah, we can fabricate lenses with different speeds. Yes, but it is scalable, but not to millions. Yes, probably up to thousands. Regarding printing on fiber sites, yes, this is possible, and actually this is also one of our products. So what we also provide is site fiducials, so or reference markers, because sometimes it is difficult to align your fiber array. Or several testing companies use top view camera in order to align the fiber with the reference marker, and we also print reference markers on the side of our fibers. So this is totally possible, yes.
Thank you.
And Matt.
Hi there. Yeah, super interesting. What was the question I had again? When we're talking about capturing, for example, fast axis light from an edge emitting diode, that's relatively high divergence. So just wondering what the refractive index of this polymer is that you're using.
So the refractive index of the polymer is more or less the same as fused silica glass, around 1.5
Right. Okay, cool.
at telecom wavelengths.
So do you have any sort of high angle means of capturing some of this higher angle output from the fast axis of a laser?
We do not have ready solutions, but I think yeah, we need to think how we can design it. And basically, I think it should be possible. Yes.
Do you have the ability to make air gaps and sort of multi-elements, or is it just the single front facet?
Yes, yes. Basically, what people also use, they can print diffractive optical elements instead of refractive, and then you can print any kind of and perform any kind of beam shaping as well, also attached to a fiber arrays.
Okay.
It's not only limited to just single block of polymer. Yeah, it's really a artificial shape, artificial design.
And final question, Elena.
I have a question about the materials from which you can print lenses on the fibers. Can it be only classical polymers, or maybe it should be something like more like fused silica?
This is very interesting question. So classically, it's only polymer, but recently there was an article, and they actually it's not Keystone Photonics, but generally in 3D laser printing, because I came from 3D laser printing background and I hold a PhD. So people can actually print fused silica using this method, fused silica lenses using this method. But what they do is they print them from special polymer, and then they bake with, I don't know, 400 or 800 degrees Celsius, and then you achieve a pure fused silica. So it is possible, but it's not like
Do you mean gossamer?
yes, I think so, yes.
Well, and can these elements keep the form with good precision after this high temperature?
Yes, they shrink with very high shrinkage value, up to 40%. But what people usually do is they compensate or pre-compensate the form so that after shrinkage you receive the file.
Well, can you send me some link about it? Because when I contacted about with companies using gossamer or GP silica, the problem was really shrinking.
Of course, yeah, this is my former university, Cultural Institute of Technology, yes.
Okay, thank you. Should I write my email here or?
Yeah, please, I will, yes.
Yeah, I can also introduce you by email, Elena, to
Okay.
Roman and discuss
Okay,
this.
thank you.
Yeah. Short question, Henrik.
Hello, Roman. Thank you for your presentation. I have a question to your laser writing technology. You're making a lens to a fiber. Is that lens written to the lens or fiber off the wafer, or is it done with the wafer and the fiber in alignment?
We do not use wafers during printing. So what we do is we attach fiber arrays to our holders and we print ourselves. So we do not use any wafers or any additional materials except for fiber arrays.
Okay, so it means that if you can position a micro lens on a fiber, we need to align that to our wafers.
Yes.
Okay. Yeah. Okay. Thank you.
Thank you, Henrik. Is a new question, Matt, or it's former?
I do have another question, yeah, if that's okay. We're not running out of time.
Last question.
It's somewhat related to Henrik's question. I mean, I'm thinking about if you had a trench and you could drop a little block 3D printed block into that trench that would have an upturned mirror basically within the wafer, then you could, create an upturned mirror as a wafer scale device. But do you see any way of sort of disconnecting, creating a lens structure within a fiber array and then disconnecting that and putting it within the wafer instead?
Yeah, yes, I know that actually our 3D printer provider, Vanguard Automation, kind of provides printer for exactly this purpose. So what they do is they print directly or provide solutions for printing directly on fiber chips, for photonic integrated circuits and for so lenses attached to wafers. We do not currently have solutions, but we also researching possibilities going into this market as well. But
sorry, what did you say your system provider was?
Vanguard Automation.
Vanguard. Okay. Thanks very much.
Good. So thank you again, Roman, for the presentation and the discussion. And we can go with our final speaker today. So sorry, Alexis, that we are a little bit out of the schedule. It's a pleasure to see you again after San Francisco. And as I mentioned, it's great to have him to give us an overview of opportunities, trends, and ideas for future in fiber sensing. So Alexis, feel free to share your screen and share your ideas with us.
Thank you. Let's see. Here. That way. It goes into presentation mode and then.
Good. Everything good now.
There we go. Well, good morning, good afternoon, and good evening. And I know, conscious of the time, we are at the end of the day, different time zones. So thank you for the invitation. Pleasure to be here. My talk will have a different coverage. So I'll be focused more on the commercial opportunities, the commercial status, some of the trends and some of the challenges of exploiting optical fibers and fiber sensors for industrial applications in different segments. First, I'll draw a contrast to the existing industrial sensing market and how much of that is fiber optic sensors, and then draw some conclusions of why would it be valuable and necessary to use optical fiber sensors for a variety of industrial sensing applications. I'll illustrate some examples that may be somewhat repetitive to what previous speakers have mentioned, and then I'll give my take on where I see potential future opportunities, and we'll wrap it up. So, present commercial status. If you look at the global market for sensors in general, different marketing agencies like BCC will tell you that by 2026, it's roughly 250 billion with a B dollars a year. And obviously, this is segmented across different industries, application segments. But as you can see in the graph here in the pie chart, by far the largest one, obviously and intuitively, should be industrial sensing with roughly 37%. So as you can see, there is at least $30 billion annually of expenditures related to industrial sensing. And sadly, fiber optic sensors don't make a significant dent out of these $30 billion. So there is an incredibly large market that is not fully tapped, and this is a nice opportunity for fiber optic sensors and photonic sensors in general to exploit that market. If we break it down into more detail, just the industrial segment of this global sensors market, obviously it has its own segmentation into true manufacturing, process control, automation, and then the usual segments that we are more familiar with for fiber sensors like oil and gas, energy and power, and to some extent chemical and mining. So you see here the segmentation. So roughly right now we are sitting at 20-some billion dollars, but it's expected that we'll reach around 50 billion by 2030. Now, in terms of which parameters are the most popular, you can see here in the pie chart that obviously temperature, pressure, and force, strain, torque are some of the three top parameters that will be the most popular. But there is a broad variety of different physical and chemical sensors that are needed for a broad variety of applications in sensing. And again, just to draw the contrast of how poor the penetration is in industrial sensing of fiber optic sensors, we can look at the breakdown of strain gauge sensing technology. This report is dated, it's from 2007 by Frost and Sullivan. And at that time, they were estimating that the global market for strain sensing equipment was on the order of $3 billion. And out of that, only 3% or 100 million were being supported by optical and fiber optic sensing solution. So the sky is the limit. There's obviously a lot of market share that can be gained by fiber optic sensors. It's just a matter of having the right solutions at the right price point and with the right features. And fiber optics has demonstrated that this is very achievable. And fiber optic sensors have had significant milestones and success stories across different application fields, whether it's fiber optic gyros, high current, high sensing in the electric utility industry. And one of the case studies that it's been more significant, more popular over the last 20 years has been the strong adoption of fiber optic sensing in the oil and gas industry. So this market peaked around 2014. At the time, there was a global business of $400 million among specialty fibers, specialty cables, downhole sensors, distributed sensing, connectors, etc. And this got to be very pervasive across the oil industry. Thousands of permanent downhole installations, hundreds of thousands of DTS, and more recently, DAS surveys. So if we were able to do it for a really harsh, really challenging industry like the oil and gas, certainly we can do the same for a variety of opportunities in the industrial sector. So traditionally, fiber optic sensors have run the gamut of a variety of different applications. Mentioned oil and gas. Previous speakers talk about wind turbine blade monitoring. Obviously, there is lots of opportunities in aerospace, like the overheat detection in civil aircraft that Proximian talked about. The defense sector has also been attractive for fiber solutions, not to mention structural health monitoring, transportation, biomedical applications. But if we really look at what is the true segmentation and the true commercial reality, as you can see here for the case of single point type sensors, whether they are FBG, Fabry-Perot, or any other type of fiber sensing technology, about 9-10% of the total global market is for industrial applications. So there's still a lot of room to growth. Most of the single point market is dominated by fiber optic gyros. It's over $500,000 to $700 million a year market globally, gyros, and everything else is fairly segmented. But you can see here that the trends are changing, whereas in 2015, oil and gas and some other applications like civil structure monitoring were dominant. Nowadays, some of those markets are shrinking. Technologies have already been developed and adopted, and there is an interest to grow both the biomedical sector as well as the industrial one. So we see here there is some growth, but I expect that as the other applications come and go, people will start paying more attention to industrial applications and develop new solutions. The same can be said of the distributed sensing side of the industry. DTS, DAS, DSS solutions for a variety of applications. Again, historically, this has been dominated by the oil and gas sector, some defense, security, monitoring applications. Sadly, the industrial side remains very, very small compared to the rest of the solutions. The same is true for the more recent and hot market of distributed acoustic sensing DAS. You see that some of the preferred applications revolved around transportation, security, seismic, mining, monitoring, carbon sequestration, but very little related to process control, industrial sensing. So even though these segments are relatively small, it also intrinsically implies that there is a lot of room for growth, a lot of room for opportunity. And in a way, there's been a unique and really outstanding success story of fiber optic sensors in the industrial segment. And this one is a Canadian company called Photon Control. Whether by design or by accident, they ended up identifying the killer application, the killer app. And that basically revolves around doing temperature sensing of the support chucks for plasma etchers in semiconductor wafer manufacturing equipment. Their technology is based on phosphorescent temperature sensor probes with very simple PLC type readout detectors. This company was acquired back in 2021. It has been the single largest acquisition of any fiber optic sensing company at $387 million. And prior to their acquisition, they had revenues on the order of $60 million a year Canadian. Over here, you can see historically some of the most significant acquisitions of companies in the fiber optic sensing space, and not even the acquisition of OpSense in 2023 at $250 million comes close to the 387. So if you identify the right application where fiber optics makes the most perfect sense, you not only can make a lot of money, but you could be the target of a nice acquisition. So why industrial sensing? Well, the reality is that if you look at any manufacturing plant, if you look at the fabrication of any specific product, whether it's in a heavy industry, food industry, pharmaceutical, textiles, materials, etc., you have an incredible amount of sensing and monitoring to do to perform control, to ensure safety of processes of personnel, to carry out predictive maintenance of the equipment, the infrastructure, also to have a more energy efficient production and reduce your costs, and certainly for quality control. So sensors by themselves are very pervasive across the industrial segment, and there is a need for a broad variety of different sensors, from temperature to pressure to strain, load, position, gas, humidity, presence, you name it. And this is such a large commercial opportunity that obviously there is a large pre-existing ecosystem of suppliers, vendors, developers, system integrators, and you'll obviously recognize a lot of the names here. So on one hand, we have our work cutoff for us because there is obviously well-established players that have broad portfolio of conventional electronic or electromechanical sensors. And as you can see here, there is a broad variety of different types of sensors, but that is not to say that fiber optics cannot do it. You see here on the upper corner a broad set of different types of temperature and strain sensing FPG sensors. So the trick here is to identify for your given company, your given process, your given technology, what would make the most sense that you can do with your own solutions based on fiber optics versus the specific needs and technical requirements of that industry. The other key trend here to recognize is that more and more we are seeing the convergence of the so-called Industry 4.0, which is a blend of sensing, monitoring, control with artificial intelligence tools, with a lot of data analytics, with robotics, smart automation. And obviously, a key ingredient in all of this, the eyes, ears, fingers of any process are sensors. So one way or the other, sensors will be required. It's just a question of how can fiber optic sensors play within the envisioned environments of an Industry 4.0. And the answer is very simple. When you visit a factory, if you know about process control or automation control, sensing in an industrial setting, you'll quickly realize that everything revolves around PLCs, programmable logic controllers. So a lot of the ovens, valves, switchers, anything and everything that is done in an industrial setting is directly or indirectly monitored, controlled through a PLC and an SCADA type environment. So the trick is make our fiber optic instrumentation seamless with this type of system. And luckily, some companies have had that vision. They had identified these needs. And one of the very first products to address this was the distributed temperature system by Yokogawa, the DTS-X, back around 2010, where they developed a Raman DTS system that was fully PLC-based. So every building block of the system, whether it's the main controller, the multi-channel unit, the power supply, the processing unit, are all separate PLC pluggable piece of modules that then can easily interface through the software that they developed into any industrial PLC environment. Another similar example is the MESCO FBG hotspot temperature monitoring system for power transformers. This is technology developed by HBK in Portugal. And here you see the three key building blocks. Again, it's a PLC-based system interrogating FBG temperature sensors, but all the data is processed and seamlessly transferred to the rest of the electric utility SCADA system through this instrumentation. And finally, there are new players, there are companies that are also keeping an eye out for these ideas. More recently, last September, you have the announcement of Photonics in the Netherlands and Gartner Instruments that they are collaborating together to basically make the FPG-based interrogators of Photonics be seamless with this PLC and Profibus EtherCAT type of industrial SCADA system. So obviously you see that little by little we are heading that way. Now, what are the actual applications, the actual opportunities for industrial sensing for fiber optic sensors? I have identified several areas. This is by far not complete, but these are some of the areas that are easier to reach, the most popular, the most common. So on one hand, again, process control. you need sensors for temperature, pressure, level, flow, force, strain, torque, you name it. So any type of conventional sensor, you can, for harsh environment applications, for multi-point sensing opportunities, you can try to develop your own fiber optic equivalents. Earlier, Proximion talked about their solution for the heavy industries, steel casting, forging, rolling, all sorts of heating, melting, and annealing furnaces. The same is true for the glass industry, all the fabrication of wine bottles, soda bottles, containers. The glass industry is also very high temperature intensive and requires a lot of temperature monitoring and control, and a broad variety of other industrial processes, one way or the other, are supported by furnaces, oven, boilers that require temperature monitoring and control. If you visit any petrochemical plant, you'll see that there is a need for a lot of tank level monitoring, detection of fugitive emissions of gases or liquids, monitoring of cracking columns, pipes, manifolds, etc. And then some areas that are not as well known, but there is tremendous opportunity, is in asset condition monitoring of rotating machines, of opening and closing devices, conveyor belts, ball bearings, fire detection, and certainly electrical utility system. Evangelos presented some of the sensors that have already for many years been adopted inside power transformers, power generators. And then finally, another area that indirectly can be very nicely supported by fiber sensors is spectroscopy, gas, liquid sensing, environmental monitoring, monitoring of emissions from factory flue stacks, etc. So in some of the heavy industries, in the petrochemical industries, there is a lot of distillation and cracking columns. It becomes necessary to know the temperature profile, to control temperatures and specific points, to avoid overheating, to detect blockages, to avoid potential fires. Some solutions are already commercially available for some of these applications, like Siemens has the Cytrans TO500 system, which is based on an array of FPGs protected in a metal tube that can basically be installed along these boilers, tanks, manifolds. Earlier, Proximion talked about their solution for the heavy industry, the steel industry, where you can have different types of steel processing, whether it's casting, rolling, folding. And there, obviously, there is a need to properly control the temperature across the process to ensure the proper annealing, the proper solidifying of the materials so that the metallurgy of the final composition is correct, and you get the right quality type of cast metal. One area that, again, I think is completely unexploited at the moment is that of condition monitoring, particularly through acoustic sensing. This is very typical, very common, used in piezoelectric and other acoustic sensing devices. And the idea is that you can, over time, monitor any piece of moving, rotating, vibrating piece of equipment by listening to their specific acoustic signatures and how they change over time. And that's a way to determine how close is a specific component, a specific piece of equipment, close to needing maintenance or close to a potential failure, or even close to causing a catastrophic accident, catching on fire, exploding, breaking other pieces of hardware. So As you can see here in the graph, depending on the type of piece of equipment, it typically may be rotating, it may be vibrating, and producing certain acoustic emission spectrum. And if you have the right acoustic sensing fibers, fiber-based microphones, or even a distributed acoustic sensing system based on coherent Rayleigh, you can continuously and over time monitor a variety of pieces of equipment like large power electric motors and determine whether any of the ball bearings, couplings, rotators, stators are displaying any particular problems and basically do corrective maintenance. This has been demonstrated both experimentally using, again, fiber optic distributed acoustic sensing, and with control experiments where you have rollers from conveyor belts in comparing the acoustic emissions from a new one from a heavily damaged one. Same is true from real installations in the mining industry, other heavy industries where you can monitor in real time long lengths of conveyor belts, either with DTS or DAS solutions, by running the cables underneath the support structures and looking for areas of overheat or intense acoustic signals that will pinpoint which specific rollers are not rolling, are getting stuck, or need replacing. Other unique applications of acoustic sensing, for instance, could be applied to air conditioning systems in large factories or even commercial buildings. So if you have problems with the compressor, if you have problems with the cooling fans, etc., you can monitor all of that infrastructure with a continuous fiber optic cable that will pinpoint exactly where there may be some problems, and the maintenance engineers can go and fix that. So lots of opportunities here. Certainly what the industry demands, not only for industrial applications, but all sensing applications in general, is both sensors and instrumentation that are relatively low cost. Distributed sensing has become very pervasive across the industry with DTS, the distributed strain sensing, as well as distributed acoustic sensing. But now for some of the industrial applications, more and more there will be a need for distributed pressure sensing, DPS instrumentation, as well as distributed chemical sensing to detect hydrogen, detect hydrogen sulfide, other pollutants, detect methane for long length distribution pipelines. I think historically the fiber optic sensing industry has overlooked the food and the pharmaceutical industries. Lots of opportunities there for sensing, for process plant control. And certainly several companies have already made inroads into heavy industries, but there is a lot more to be done, lots of opportunities there. And we cannot overlook opportunities brought on by green technologies, environmental sensing, pollution detection, etc., mostly centered around gas sensing solutions. One key thing not to overlook for industrial applications is that oftentimes these involve harsh environments. There's lots of dust, water, high temperatures. So the fibers, the cables, the specific sensors need to be high temperature resistant. They need to use the right protective coatings, whether they are metal coated fibers, ceramic coatings, protective sheets, and certainly the connectors, the rest of the packaging of the instrumentation needs to be rugged to survive long term in these environments. And as I mentioned earlier, one way or the other, whatever is done in an industrial setting will need to be a part of the rest of the SCADA system of that plant, the supervisory control. and data analysis system of that. So we need to figure out how to extract data from our fiber optic instrumentation and make it seamless into these SCADA systems. And that also involves making things simple to run, plug and play, as opposed to needing a PhD in optics or electronics to figure out how to calibrate the sensors, how to enter data into the software provided by the vendor, and get everything up and running. And of course, prices remain relatively high compared to conventional technology. So there's got to be a cost reduction effort here. So in summary, there is at least $30 billion a year in industrial sensing, and this is expected to grow to 50 billion by 2030. So large market opportunity. It's in my personal opinion, very untapped by fiber optic sensors. So the sky's the limit to what we could do for industrial sensing. And sensors, fiber optic sensors themselves lend themselves very nicely for opportunities in this sector by their unique features for multi-point sensing, multi-parameter sensing, distributed sensing, their intrinsic safety and immunity to electromagnetic radio frequencies. So these are the key characteristics that would beat the conventional electronic sensors. However, again, we need to make the devices rugged, seamless with the SCADA systems, and certainly the cost. I mean, some sensors can be a factor of 2 to 5 times more expensive than a conventional electronic version. So I appreciate your attention and staying late in European time, and thank you, and enjoy the rest of the day, and happy to answer any questions. So.
Thank you, Alexis. Is there any question or comment? You mentioned in the challenges both the need of developing solutions and on the other side having more cost-effective solutions. But do you think that there is also the work to research in these kind of sectors or industry, understand the challenges, see where there are opportunities? Do you think there is some room to work in this direction, or more or less is clear and it's a question of developing new technologies and having them in a lower price?
I think it's the fact that as a community, I mean, the fiber optic sensing community, we all come from either an electrical engineering, an optics, photonics background, R&D background. We come from a sheltered background, not necessarily from an industrial one, meaning that, I never set foot in a steel casting or a rolling plant in my life, right? So, and I wouldn't know the first thing about how do I engage with someone from that industry. So in my mind, I think one of the reasons why we haven't tapped the industrial sector is because it sounds too different from what we are used to. And it may not be as sexy, as nice as dealing with biomedical or dealing with aerospace, even oil and gas. So I think the exercise is more of approaching those customers first and learning about what problems they have, what needs for sensing monitoring they have that could potentially be addressed with fiber optic solutions versus conventional ones, and then see if the technology could simply be tailored to meet those technical requirements without necessarily having to develop something from scratch.
Very good. Don't know if there is any other question. I know that it's late, so I appreciate that Alexis can share all this information with all of us and also all the attendees and the rest of the speakers. So I think we can close the meeting now. we drop a poll, so the answers are really welcome. And again, thank you to all the speakers, to all the attendees, and feel free to contact me if there is any interest in contacting some of the participants for further discussion. We can make an introduction by email. So have a good rest of the afternoon, evening, and see you in the next technology meeting.
Thank you. Bye.
Thank you. Good afternoon, everybody.
Thank you very much. Bye.
Thank
Thank
you.
you. Thank you very
Thank you very
much.
much.